Hello and welcome to Statecraft IAS Academy. I'm Atif, your geography educator. A research was conducted in Stanford and the results were just groundbreaking. Amazing results. Yeah, if you take a look at this slide, scientists map rare earthquake deep within Earth's mantle. This is actually very amazing. It might not look that important, but it can actually change our understanding of the interior of the Earth. Let me tell you first, our understanding of the interior of the Earth is based on indirect sources and not on direct sources. We have not dug deep enough to go to the interiors because of high temperature, high pressure. So whatever information we have is based on indirect sources. It can be wrong. And this article has actually changed our perspective. We might actually learn something new about the interior of the Earth. That is why I told you that this is going to be groundbreaking. Yeah, you heard me correct. Today I'll tell you why this research is important. What is the meaning of earthquakes in the mantle? But before we go deep into the mantle, we should know what earthquakes actually are and where they are located as of now, as per our understanding. Once we understand the earthquakes as we know as of now, then only we will know about the mantle and the earthquakes present there and how they can actually change our perspective. Now, let's start with the basic interior of the Earth. Well, all of us from class 6th know that Earth consists of crust, mantle, and the core. Well, if we want to divide it a little bit more, we can divide it into the crust into two parts, upper crust, the lower crust. Then mantle into two parts, upper mantle and the lower mantle, and core in two parts, outer core and inner core. Now, the article that I just discussed talks of earthquakes located in the upper mantle region. Where exactly? That we will discuss. So before we go to that portion, let me just give you a brief overview of the parts of the earth more specifically so that you are able to link the things. And then we will go to our research paper. Listen to me very carefully. I'm going to draw the interior of the Earth. First layer, the crust. Okay? And the crust is divided into two parts. The upper crust or the outer crust and the inner crust. These are the two parts. Then we have the second layer, that is the mantle. Now, mantle is again divided into two parts, but this layer is very much important for us. So kindly pay proper attention to this layer. Okay? I'm going to draw this a bit more bigger. Okay, so when we talk of mantle, we have the upper mantle and the lower mantle, and finally we have core. Now, you should pay attention here. Core is not that much important for us, so I'm not going to draw it in two layers, although it is also of two layers, the outer and the inner. But right now, our area of concern is only this much. That is the crust and the upper mantle. Okay, if I draw it like this, the outer mantle and the upper mantle, take a proper look at this. See, this is the upper mantle and this is the lower mantle. Lower mantle is not important for us right now. If you take a look at this image, see, it's showing that we have the crust, that is the very thin layer of earth. It hardly goes up to 70 kilometers maximum. That's maximum. It won't go beyond that. Then we have mantle. The mantle goes up to around 2900 kilometers. And the core, that's the radius of the earth eventually, up to 6371 kilometers. We are concerned with upper mantle, that is up to a depth of 700 kilometers. Remember this, the upper mantle ends at around 700 kilometers. This is a rough estimation, of course, but it ends at around 700 kilometers. Now listen to me very carefully. The upper mantle is further divided into certain parts. the uppermost part of the upper mantle. I'm talking of upper mantle. The uppermost part of the upper mantle is solid. It is in solid state. Under the solid state, under the solid layer of the upper mantle, we have a semi-solid layer here. This layer is semi-solid, or we call it as asthenosphere. Then after that, we again have solid layer here. And finally, in core, we have the upper core or outer core as liquid and inner core as solid. Well, I told you already, core is not our concern right now. All we need to know is about mantle, because we have to learn about the earthquakes present in the mantle. Now, keep this thing in mind. The crust is completely solid. The crust is completely solid. The uppermost part of the mantle is also solid up to this level. This is also solid. After this, we have a semi-solid layer, which we call as asthenosphere. You know what semi-solid is? Not fully liquid, not fully solid, but a state in between. It is semi-solid. Okay, now one important thing that you need to know here is that when we combine these two, that is the crust and the solid part of mantle, that's why I told you to pay attention properly. When we combine these two parts, the crust and the uppermost part of mantle, that is solid, this is known as lithosphere. Am I clear? Any confusion? If you have any confusion, then let me know. Listen to me again very carefully. Dividing the earth, we are considering the parts of earth as the crust, mantle and core. Crust being completely solid, the uppermost part of the mantle being solid, and then after that, in the upper part of the mantle only, in the upper mantle, uppermost part. Let me tell you here, when we talk of crust, it is completely solid. When we talk of uppermost part of mantle, uppermost part of mantle is also solid. And after that, the rest of the upper mantle, we can say up to 200 to 300 kilometers, is asthenosphere. It is also part of upper mantle. After that, we have lower mantle, that is solid. Then we have outer core, which is liquid. We will not go into that much of detail. These two are known as lithosphere. The solid part. Lith means earth, the rock. So the lithosphere includes these two solid parts. If you take a look at this image, you can see here, this is the crust and this is the mantle. This is the crust. And this is the rigid uppermost part of mantle, as I already told you. The rigid uppermost part of the mantle plus the crust is known as lithosphere, as is mentioned here. But after we go down, we reach to a layer known as asthenosphere. Am I clear? And this is the layer that is neither solid nor liquid, but it is semi-solid in nature. This is very important. I am stressing on this thing because this is very important for you to understand. Now, when we take a look at Earth, this is the map of Earth. The entire Earth is made up of lithospheric plates. What does that mean? If this is Earth, let's say this is Earth, it is made up of different plates. One plate here, then second plate here, third plate smaller, fourth plate larger. There are many plates, minor plates, major plates. There are a lot of plates that are present. Just give me a second. Okay, so a lot of plates are there and we call these as lithospheric plates. This is an image that shows the lithospheric slabs or the plates. Entire Earth is made up of these slabs. This is India. India made up of Indian plate. If you're not learned about the movement of Indian plate, formation of Himalayas, we can learn about that as well. But right now, let's say you know about these things. So these are plates that make up the earth. Now I want to ask you something here. Talking of these plates, they are located on something that is semi-solid. Okay, what is semi-solid? Asthenosphere. What will happen? This semi-solid layer will keep moving. It will not be stable. It will not be stable. Just imagine a bucket of water, a tub of water. When you put something like a wooden block in this, what's going to happen? The log will start to float here, there, it will start to move. Why? Because it's not present on something solid but liquid. Similarly, this semi-solid asthenosphere will make sure that these lithospheric slabs are not stable. They move around. They go from here and there. And this is what actually is happening in the interior of the earth. We have convectional currents that are present in the interior of the earth. And they cause the movement of the plates. How? Let me show you how. Look, let's say we have one lithospheric plate here, one lithospheric plate here, and then underneath we have semi-solid asthenosphere. In semi-solid asthenosphere, we have constant movement like this. Correct? Same here. This is the convectional current theory. I hope you know about it. If you don't, then we can learn about it. That's not an issue. So whenever there is a movement like this, the plates will move in this direction, away from each other. Or we can have one more thing, that is direction like this in the interior of the earth. Then the plates will start to come towards each other. Long story short, we have a semi-solid layer that causes these lithospheric plates to be in a constant motion. They are not stable. It's not that the lithospheric slab is present somewhere and it will remain at that place. For example, this Indian plate has traveled a long way. If you know about the geological history of India, it was once located here somewhere. Then it traveled and reached here eventually. Why did it travel? Have you ever thought? You might have heard of traveling of Indian plate. It traveled because it's placed on a semi-solid layer that causes this plate to move constantly. It does not allow it to be stable at one single place. Very important. Now, tell me something. These are rocks that we are talking of. Lithospheric slabs. What are these? Rocks, solid blocks of earth. What will happen when there will be a movement? Listen to me very carefully. Let's say these are two rocks. The rocks are not, they are like this. Then we have rocks like this. And they will be in motion because of the convectional currents or the asthenosphere. Because the rocks are heavy and they will interlock with each other, they will resist this motion. Because of these convectional currents, the rocks resist this motion. What is the meaning of resisting the motion? They do not move. They try to push. For example, somebody is trying to push me and I'm holding him. He's coming and trying to push me. I'm holding him. I'm trying my best not to get displaced from my place. I'm holding my ground. Same is the case with these rocks. They try to hold their ground and not move. They try to resist this motion. Like I am trying to resist someone if somebody is trying to push me. But a time will come when the force will be too much, the force will extend. It will be so huge, the rocks will not be able to resist the motion. Or, as I told you, somebody is trying to push me, but I can stop it up to a certain extent. After a certain limit, I will not be able to stop him. Let's say 2 people or 3 people are trying to push me. I will not be able to stop him and they will push me. More I apply the force, more they will try to push me and eventually I'll be thrown back. Same is the case here. When the motion of the rocks start and the resistance is not enough to prevent the motion, what will happen? For example, we have rocks here who are trying to resist the motion. But now the force has become so huge that the resistance is not possible. What will happen at that time? the energy will be released from these places. There will be huge release of energy. A huge release of energy will take place, and it will lead to formation of cracks, faults in the rocks. For example, this is a rock which was trying to resist the motion, but eventually the energy became so huge that at this very point, where there might have been some sort of weakness already present, because there are weaknesses that are present, the joints, the cracks. Let's say this is a point where a little bit of weakness was present. So this portion was not able to resist, and there was a huge release of energy, and cracks will develop. Cracks will start to develop. And this release of energy leads to shaking of the ground. When such huge energy is released, it causes shaking of the ground and eventually earthquakes. Did you get the geology behind earthquakes? It's not simple shaking of the ground. It is basically a condition where the resistance offered by the lithospheric rocks is not enough to hold the ground. It causes the shaking of the ground and eventually earthquakes. Take a look at this image if you want. This shows a region or a place here where the faulting takes place or the rocks break. Why? Because the energy is released from these areas. The rocks are not capable enough to hold it. See, the lower layer is the asthenosphere on which the rocks move. This is the convectional current, the arrows here. Earlier, the rocks tried to hold their ground. They tried not to move. But a time comes when they will not be able to hold on. They will succumb to the pressure. And that is the time when there will be fracturing or cracks developing, energy released, and earthquakes. Now, before we go ahead, let me tell you a few points about earthquakes that you should know. The place where the initial fracture takes place, where the energy is initially released, it takes place deep inside the ground. For example, let's say this is the ground and this is a place where the faulting takes place. It starts at this place. This region will be known as hypocenter. It is located within the earth and it is known as hypocenter. Number one. After the energy is released, it will travel in all the directions. It will travel in all the directions. Correct? And it will travel towards surface. This is the surface of earth. Let me draw some houses so that you don't get confused. Or let me draw a tree here as well. Well, the tree is not good, but let's say this is a tree. Okay. So this is the surface. The first place where the waves will reach on the surface. This is the shortest distance between the focus. Hypocenter is also called as focus. It is the same. Whether the word focus or the hypocenter, it means the same. They are synonyms. The first place on the earth where the waves reach, obviously they will reach here because it's nearest to the focus. This is known as epicenter. What? Epicenter. Now listen to me very carefully. When I'm talking of epicenter and hypocenter, don't get confused between the two. Epicenter is a point on the surface of the ground, on the surface of earth. Hypocenter is a point that is located deep inside the earth. Well, it can be deep, it can be not that deep, but let's say within the earth. It's not on the surface. That is the diagram that I'm showing you here. This is the focus or the hypocenter inside the earth where the rocks started to fracture, where the energy was released. And when you take a look here directly on top of the earth, somewhere here, this is epicenter. Understood the difference? Now, one important thing that I also want to tell you here is once the energy is released, the waves are released in all the directions. What is energy? What are waves? Waves are basically energy. The energy is released from these places where the earthquakes take place, from the hypocenter, not from the epicenter. The waves are released from the hypocenter and they travel in all the directions throughout the earth, within the earth, on the surface of the earth, depends upon the intensity. They travel all along the earth. And these seismic waves are very important in understanding the interior of the earth, and these are the waves that will eventually help us in understanding the mantle earthquakes. How? Question, how? No problem, I'll tell you how. Listen to me very carefully, this is a very good thing. When we talk of waves, earthquake, we have two types of waves. Two types. One is called as the body wave, and the second is called as surface wave. What is the difference? As the name suggests, body waves that travel within the body, that travel in the interior of the earth. Surface waves, the waves that travel along the surfaces. Simple as that. But these are further divided into two types. When we talk of body waves, we have P or primary waves and S or secondary waves. Surface waves, Rayleigh waves and love waves. Surface waves cause maximum destruction. They cause damage to houses and all, but right now we are concerned with body waves because these are the waves that will help us to understand the interior of the earth. Primary waves are named as primary waves because these are the first that are detected on a seismograph. They travel very fast. Primary means the first. They are first detected. They have certain properties. Like what? First of all, they have more speed as compared to S wave. They travel with expansion and compression. What is the meaning of that? That means they will travel somewhat like this. Compress, expand, compress, expand, compress, expand, compress and expand, and continue to move like this along their movement. So they will displace particles parallel to the movement of the wave. What is the meaning of that? That means the wave is traveling in this direction. So particles are also getting displaced in the same direction. Number one. And the second and the most important property of P waves is that they can travel in solids, they can travel in liquids as well as in gases. Of course, the speed is more in solids as compared to liquids and then as compared to gases. But they can travel in solids, liquids and gases. And then we talk of the S waves or the secondary waves. They travel like this. They displace the particles perpendicular to the direction of propagation of wave. Number one. And number two, they only travel in solids and not in liquids. Am I clear? This is a very important property that will help us to understand the interior of the earth. Number one, the P waves will travel in solids, liquids and gases, and the S waves will travel only in solids. We are not going to discuss surface waves right now because they are of least significance as far as our topic is concerned. Now, let me draw a diagram of the earth, let's say interior of the earth. Okay. Remember, this is the boundary between mantle and core, and this is the boundary between outer and inner core. Let's suppose, let me change the color, or let me change the color first so that you don't get confused. Let's suppose an earthquake takes place at this region. Here, the waves will be originated, P waves, S waves. First, we will talk of P waves. When the waves will start to travel, they will travel somewhat like this. When the waves will reach here, what's going to happen? This is a liquid layer. You know about refraction. You learned in physics about refraction. Whenever a wave passes from one medium to another medium, what happens? It bends. So when it will pass into the liquid, it will start to bend. It will go like this. Then it will come out of this and again travel like this, bend again and reach here. Similarly, a wave will come from here, bend like this, take a second bending here. Why? Because the inner core is solid. Then bend again and come out. And this process will continue. This process will continue. I'm talking of P waves. Red is for P waves. Now I want to ask you something. Okay, this is P waves. What will happen with the S waves? The S waves will also originate from same region. They will travel like this, reach here. They will travel like this, reach here. But when the S waves will reach here, they will not be able to penetrate this. Why? Because I repeatedly told you the S waves will only travel in solids, and this is a liquid layer. The outer core is a liquid layer. If you don't know about the interior of the earth, let me know in the comments. I will bring one full-fledged class on the interior of the earth to make you understand. Right now, remember that outer core is the liquid layer, but S waves will not be able to propagate because they will stop here. They cannot pass through this. They will be stopped. They will only pass through solid media like this. But when we talk of P waves, they will travel all of the interior of the earth, everywhere. They can pass through everything because they have this property. This is a property that helps understand the interior of the earth. And what we witnessed is that P waves are absent in only this region. They are present here. They are present all along these areas, everywhere. But S waves are located only in these regions. S waves, P waves, P waves, P waves will be present everywhere, but S waves will be only present here. So this gives us the concept of shadow zone. What? Shadow zone. What is a shadow zone? Take a look at this image first. This shows the black lines show the S waves. They are located all along, but after 105 degrees, we have 0 S waves. But when we talk of P waves, from 105 to 140 degrees, we do not have P waves. But after 140 degree, again, we have P waves present here. You can see these are the P waves that are present, but S waves will stop here. That shows us the presence of different material located within the interior of the earth. This helped us to understand the interior of the earth. If you want to learn in detail about the interior of the earth, we can bring a separate class on that. Right now, all I wanted to tell you is how the things take place in the interior of the earth, how the waves propagate. Why? Because now we are going to the earthquakes located in the mantle. When I told you about the earthquakes, where did I tell you? This one. This image. You can see this is asthenosphere. Okay, this is asthenosphere. The earthquakes take place in the lithosphere and not in the asthenosphere. You should know that. They do not take place in the asthenosphere. In the upper part of the mantle only, uppermost part of the mantle, the earthquakes take place. But now, a research has shown that the earthquakes do take place in the mantle. Beyond the Moho discontinuity. What's a Moho discontinuity? Moho discontinuity is a discontinuity that separates the crust from mantle. That means around 60, 70, 80 kilometers beyond this level in the interior of the earth, somewhere in asthenosphere, the earthquakes take place. Well, how? We don't know, because this is a semi-solid layer. But let's look at the research paper that was published. First of all, let me give a summary of the paper. Stanford researchers have created the first global map of rare continental mantle earthquakes. Earthquakes usually are considered to take place along the boundaries of the plates, lithospheric slabs, continental plates, oceanic plates. These researchers have also shown that the earthquakes take place at specific locations, although they might be located throughout the earth, but there are some locations that witness more mantle earthquakes. Take a look at this map. This is the global map of continental mantle earthquakes, published by Stanford University Research. Rare deep events more than 80 kilometers below Earth's crust. And what are the two regions where they witnessed maximum mantle earthquakes? Number one, the Himalayan region here, and number two, the Bering Strait. You know what a strait is? Bering Strait is a strait located between Russia and America. More specifically, you can see Russia and Alaska. There's a strait known as Bering Strait, and these are the two regions where maximum mantle earthquakes were observed. This was the first point of this research. Second, study finds deep earthquakes clustered beneath regions such as Himalayas and Bering Strait, as I already told you. Okay, maximum earthquakes clustered in this region. And the method they used distinguishes mantle quakes from crustal ones using seismic waveforms. They also used waves to understand them, but they used two different types of waves. We don't have to learn about those waves, that's not our concern, but we should know that this is something that was used. That's why I explained you the waves as well, so that you don't get confused. You already know about P waves, S waves, surface waves, body waves, everything. But here I'm going to tell you two different types of waves. Let's take a look at the paper. What are they mentioning? If you take a look, this is a screenshot from the paper itself where they published their research. And you can see for decades, scientists debated whether the mantle could host earthquakes at all. That's what I was telling you initially. There was a huge debate whether mantle could actually host earthquakes or not. Because what I told you is that once the rocks break, because they cannot resist the movement, they try to resist it. But when the resistance fails, there is a friction, there is a release of energy which causes earthquakes. But imagine water or any semi-solid medium. You have jelly. Let's say jelly. You like jelly or not, I don't know. But let's say jelly. What happens? There is no friction in that. It cannot resist the movement. So ideally it was believed that that is a semi-solid place. So is it even possible for the mantle to host earthquakes or not? This was the first question, because the material there is totally different. What we understood as an earthquake was primarily because of the breaking of rocks, creating of faults, friction created between the rocks. Okay. While the deep earthquakes are well known in subduction zones where oceanic plates sink, this is the crustal continent. I am going to bring next class on the plates and plate boundaries and formation of various subduction zones. I will bring one class on that because that's a very important class, and that's also in news because of a very strong earthquake in Russia's Kamchatka Peninsula. But right now, what I'm trying to tell you here is that over the past decade, most researchers have accepted that such earthquakes do occur. That is, they believed, yeah, there might be mantle earthquakes. But what's the catch? They did not have enough technology. They could not identify them. They didn't have enough research, enough data to back this thought that whether actually the mantle earthquakes are a fact or not. They although believed, yeah, that can be a possibility, but it was actually proved by the Stanford research. The name Wang and Klemperer, these are the two people who discovered this. They used a method, they developed a method. Can you imagine this research? This is something that is novel. There is not something that has taken place like this in the past. This is happening for the very first time. A method is developed. Not only the results, but also a method is developed that compares two types of seismic waves. Now, this is a very important thing that I want you to listen. Two types of seismic waves. Till now, I told you about body waves, surface waves. Body waves as P waves, S waves. Surface waves are Rayleigh waves and love waves. But here, they used two different types of waves. SN waves, which travel through the top of the mantle. Listen to me very carefully. SN, not S. This is SN. This is not S. SN waves. And from where they will travel? Through top of the mantle. That's their direction, their location where they travel. And LG waves, which move easily through the crust. So, SN, top of mantle, and LG through crust. The relative strength of these waves allows scientists to determine whether an earthquake originated in the crust or the mantle. How? Now imagine an earthquake taking place in the mantle. Listen to me very carefully. This is something that you need to observe. Imagine an earthquake taking place in the mantle. So which wave will be more predominant? Which wave will be strong? It will be Sn, because this is the wave that will travel in the top of the mantle. But when Lg waves are strong, then we might assume that these are crustal earthquakes. But if we have predomination of Sn waves, then we can imagine, okay, this might be a mantle earthquake. And that is exactly what this research has done. The relative strength of these waves, that relative strength means whichever wave is stronger of the two. Relative strength means among the two. Whichever wave is stronger among the two determines what type of an earthquake it is. And that's what he mentioned. Our approach is a complete game changer. Because now they can actually identify a mantle earthquake purely based on waveforms of earthquakes. This shows the research, the level of research. They analyzed more than 46,000 earthquakes recorded since 1990. It's not a cakewalk. These many earthquakes for the past 35 years, and narrowing down to 459 earthquakes. Just imagine, out of 46,000 earthquakes, 459 earthquakes were confirmed to be continental mantle earthquakes. That means as of now, as per our not our research but their research and the data available with us, there were observed 459 continental mantle earthquakes. And they said that this is a conservative figure and there can be much more. They found this much. They were sure of these many. There can be many more, but they were sure of 459 continental earthquakes. Okay, but you do not have to worry about anything. You don't need to worry. You don't have to stress that there is something new that's going to cause damage. Listen to me very carefully. They said that although the earthquakes are too deep to cause serious shaking at the surface, the press release notes that studying them could improve understanding of the earthquake mechanisms. Long story short, they clearly stated here that these are too deep to cause serious shaking at the surface. That means we will not even observe them, or maybe observed at a very minor intensity, not a huge intensity. Are you getting my point? That they are so deep that they will not cause damage, but there is a use of them that they can actually help us understand the interior of the earth on a broad level. We might learn about the interior of the earth, because right now what we know about the interior of the earth, as I told you in the start of the lecture, we only know about the interior of the earth as crust, mantle, core, and because of the indirect sources we are not sure. If we had direct sources, if we were able to go deep inside the earth, then we might know more about the interior of the earth. But unfortunately, that's not possible. The science is not that much developed yet that it can actually show us. It can allow us to go deep inside the earth. We might melt after traveling just a few kilometers because, as I told you, there's an increase of 1 degree temperature every 32 meters. Can you imagine? That means once you travel maybe 1 kilometer, you might witness around 30-40 degree of temperature. Just 1 kilometer. And Earth is 6,370 kilometers radius. Can you imagine the temperature? Although the temperature does not increase that much after a certain distance, after a certain depth, but it is very high. 4,000, 5,000, even 6,000 degrees. That is why the outer core is in liquid form, because the temperature is too high there. So we cannot go inside the earth. All we know as of now is because of the seismic waves and some other sources, of course, but seismic waves are the primary sources. Now, one important thing that I want to make note of here is that here, let me point it out for you. What is the crux of today's lecture? First and foremost, what is a lithosphere? Crust plus upper mantle, uppermost mantle, not only upper mantle, number one. Number two, and the very important thing that you need to know here is that earthquakes release of energy when the force of resistance in the rocks is exceeded. That's earthquakes. Then two important points, hypocenter and epicenter. Okay. Then one important thing that you need to know here is about the waves that are released. I have got one diagram, this one for you. These are body waves. This exactly shows how the waves propagate. And these are surface waves. Take a look at both of these. I told you P waves travel like this. Compression, then expansion, then compression, and travel along this. The particles are distributed, particles move along the same direction. See, this shows here you have compression, then expansion, then again compression. Clear? And the thing continues. In case of P waves, in case of S waves, the waves propagate like this. See, the waves are propagating somewhat like this. And the particles are like this. So this is the direction of wave. So they are perpendicular to the direction of wave. In this case, they are parallel to the direction of wave. I told you not to learn much about relic wave, these surface waves, because this was not our topic of concern. But since the image is here, see the relic waves, the motion is more or less circular. See, like this. This is traveling like this, more or less circular. This also forms crusts and troughs, but the movement is more or less circular here, and they cause damage. Whenever relic waves reach the surface, you can see a bit of an up and down motion. The houses might feel like this, up and down motion, earthquake. And whenever love waves, these cause maximum damage. They distribute the earth like this, here, here, up and down. They try to disturb the surface of the earth in every possible direction. Every possible direction, up and down, right and left. That means the house will shake up and down and right and left. So there is a more chance of damage because of love waves. Love is always dangerous. Am I right? Okay. So then we discussed the waves, body, surface, primary, S, love, relic. And finally the mantle earthquakes. The mantle earthquakes, which were from Stanford University, concentrated in Himalayas and Bering Strait. 479, if I'm not wrong, 479 or 69. Yeah, 459, sorry. 459, huh? My bad. 459 earthquakes. And what was the method of study? SN waves and LG waves. These are found in mantle. These travel along the upper mantle and these can travel along the crust. This was the method used. You don't have to know anything more than this. This is more than enough for your, let's say, a 250 words answer. If you are appearing in the mains, if you're going for MCQs, you might easily be asked, what is the role of SN and LG waves? You should know what's their role. You should know about their location, ideal location. So this is something that was related to current affairs. That brings us to the end of today's class. This is the article that I got for you. If you want to learn about it, as I told you, the best place to learn about such things is Down to Earth. Is a magazine freely available, not paid. You can go to Google and learn more about this news. So that's all from my side today. Let's end our class here till I see you next time. And you can tell me in the comments as well what class or lecture you want up next so that I can bring it for you. Till then, bye bye. See you.